Let us now talk about composition of functions. So say you're given two functions, f, it goes from a to b, and g, it goes from b to c. Then we can define the composition from a to c. So let us just draw this, that will make it clear. So say you have set a right here, and then you have set b, and you have set c. So from a to b you have a function f. From b to c you have this function g. So g, and this is f. Then you have a function from a to c. You first apply f and then you apply g. So you first apply f, and number 2 you apply g to it. That's why we write g of f. So you get a function g of f from a to c. So this will be more clear in an example. So say you define, say, f of x as x plus 1, and say g of x as x square. So let us first write down set a. So say this is set a. So set a consists of elements 1, 2 and 3. 1, 2 and 3. Then you have set b. Set b consists of elements, say, 1, 2 and 3, 4. 1, 2, say 3 and 4. And then we have set c. So set c consists of elements 1, say 4, 9, 16, 25. So first we draw f. So f goes from, say, a to b. So f of x is x plus 1. So you take 1, you add 1 to it. It is x plus 1. So 1 plus 1 gives you 2. So 1 gets mapped to 2. 2 plus 1 gives you 3. So 2 gets mapped to 3. 3 plus 1 gives you 4. So 3 gets mapped to 4. Now g of x is x square. So 1 square is 1. So this 1 will get mapped to 1. 2 square is 4. So this 2 will get mapped to 4. 3 square is 9. So 3 will get mapped to 9. 4 square is 16. So 4 will get mapped to 16. Now we do the composition. So the composition is, we have to now go from a to c. So for going from a to c, you just follow the arrows. So first you write down the sets. So a has 1, 2 and 3, and c has 1, 4, 9, 16 and 25. So 1 first maps to 3 and then it finally maps to 4. So this is the path of 1. So 1 goes to 4. So that's what we are going to do here. 1 will go to 4. Then 2. 2 first goes to 3 and then it ends up to 9. So 2 will go to 9. 3 first goes to 4 and then 4 goes to 16. So 3 ends up at 16. So 3 goes to 16. So this is the composition. You first apply f and then you apply g. So let us see it computationally. So we say g of f, this is nothing but g of f of x. So instead of x, I'm going to write this thing, f of x. So this will become f of x square. What is f of x? It is x plus 1. So this is equal to x plus 1 square. So what have we gotten? We know that g of f of x is now x plus 1 square. So if you plug in 1, so you get 1 plus 1 is 2, 2 square is 4. You plug in 2, 2 plus 1 is 3, 3 square is 9. You plug in 3, 3 plus 1 is 4, 4 square is 16. So that is how you get the composition of functions. Let us do one more example. So again you have two functions f and g, from going from real numbers to real numbers. F of x is sin x, g of x is 5x square. Then f composed with g. So first you apply g and then you apply f. So instead of g you write 5x square, so f of 5x square. Yeah, so now instead of x we are going to write 5x square. So this x corresponds to this x. So this 5x square will now replace x here and you have sine of 5x square. Similarly, you can first apply f and then apply g. So this will be g of sine x. So g of x is 5x square. So instead of x I'm going to write sine x. So instead of this x here we'll write sine x. So g of sine x is 5 sine x square. So notice you can immediately see that these two are not equal. Yeah, because sine of 5x square is not equal to 5 sine x square. So these two functions are not equal. So this was all about composition of functions. Now we will talk about invertible functions. We now talk about invertible functions. So consider a function f. It goes from a to b. So you have set a here and you have set b here. So function f goes from a to b, and then you have function g which goes from b to a. So if you first apply g and then you apply f, so if you first apply g, that you go from b to a, then you apply f and you come back to b, it is same as applying the identity on b. And if you first apply f, so you first apply f, then you apply g, you land up back in a. So this is same as identity on a. Then g is called inverse of f and is denoted by f inverse. So by the same story you could say that f is inverse of g and you denote f by g inverse. So first focusing on f inverse, what we essentially mean to say is that instead of g now you write f inverse. So instead of g you write f inverse. So that means, so if you first apply f inverse and then you apply f, you will land up in b again as an identity function. On the other hand, if you first apply f, that is you go to b and then you apply f inverse, you get identity on a. So this is the property of the inverse functions. So how do we compute these inverse functions? So that is the question. So we will give an example. This is a standard computation. So say you have a function f from x to y, and g is an inverse function. So f goes from x to y and g is an inverse function. So we have to show first that, so first if you apply g and then you apply f, so you will land back in y. So you should have identity on y. So that is f of g of y is y. The second thing you want to show is that if you first apply f and then you apply g, this should be identity on x. So you first go from x to y and then apply g, you should get identity on x. So this is same as saying that g of f of x is just x. And then you can say that g is the inverse function. Then you will just put g as f inverse. So we are just following this definition. So say the function given to you is 3x plus 1. F goes from x to y. So in order to set the inverse or to find the inverse, you set y equals to 3x plus 1. So instead of f of x, we are just writing y. So instead of f of x, we are just writing y. So you rearrange and solve for y. So you say x is equal to y minus 1 by 3. And this you, instead of x, you write g of y. So instead of f of x, we wrote y. Instead of x, you are writing g of y. Now you are saying that this is the inverse function. This is the inverse function. So finding the inverse function is very easy. So this is the inverse function of f. So this g of y is inverse function of f of x. So obviously f acts on small x and g will act on small y, because f goes from capital X to capital Y, and G goes from capital Y to capital X. Now let us check this out. So first you apply G and then you apply F. So if you first you apply G and then you apply F, you want identity on Y. So we are going to confirm this part. So F of G of Y. So instead of X, we are going to write G of Y. So instead of X here, you're going to write G of Y. So you have 3G of Y plus 1. So G of Y is nothing but this function right here. So you plug this in. So you have, instead of G of Y, you write Y minus 1 by 3. Now 3 cancels out. You have Y minus 1 plus 1. You get Y. So you get F of G of Y is Y. So this thing is satisfied. Now we have to satisfy this equation. So G of F. So you first apply F and then you apply G. So G of F of X. Instead of Y, you write F of X. So you get F of X minus 1 by 3. So F of X is nothing but 3x plus 1. So you plug in 3x plus 1. This cancels out. You have 3x by 3. 3 cancels out. You get X. So G of F of X is X. And therefore this is proved. So you have G is equal to F inverse. So finding an inverse function is not a complicated task.